In this Excel tutorial, we're going to plot a calibration curve for two different students. We're going to add a linear trend line and show the equation of the line as well as the r squared on the plot. We're going to execute the LINEST function so that those parameters, the mx plus b parameters, will be in the body of the spreadsheet so you can use them to do calculations. And then we're going to determine the concentration of the unknown sample, which response is given here. So first we're going to plot the data for student A, and then we're going to plot the data for student B separately. So here I'm just going to select that whole data set. I'm going to insert a scatter chart. So you're going to want a scatter plot. And you can see that looks just like what we saw in the last tutorial video. I'm going to add quickly the axis labels. And just to be clear that this is concentration or the amount of protein. So in this case, I guess it's milligrams of protein. And then this axis is the response. So I believe this is absorption, but it's whatever the measurement is. And in this example, I suppose it doesn't matter too much. Once you have a chart or a scatter plot, or your calibration curve plotted, then you can click on the data set itself. And for me, it's a control click or a right click will get you this menu, and you can add a trend line. You can probably go to add a chart element as well, and that should pop up there. But I'm going to add a trend line, and you have a bunch of options. You can do a polynomial fit, a logarithmic fit, a linear fit. Linear fit is what you would be using for most of your measurements in this class. So that's the default. You can just leave it there. And at the bottom of this menu, you can display the equation on the chart and display the r squared value as well. If that's hard to see, you can go back to your home menu over here and change the font size. If you want to do that, you can also format this for sig figs and etc. The same way you do other types of things. So we can see student A has a pretty high correlation coefficient, 0.9938. That's really precise. You'd want to edit this axis to make sure that you're utilizing all the space and you don't have any empty space in your plot. We can plot student B as well. Okay. And I'm going to... That's a command hold for me, but I think it's control for non-max. Again, I'm going to insert a scatter plot, and you can already see that this data looks less precise than the other set of data. If I add a trend line and include the equation and the r squared on there, you can see the r squared is significantly lower for student B than for student A. So I'm just going to clean this up a little bit. Student B. Okay, I'm going to change my scale to 25. Okay, and then add my axis titles. All right, so this is absorption, and this is milligrams of protein. Okay. So student B has less precise data than student A. Either way, they both need to determine the concentration of this unknown. So they're going to take this absorption value and basically plug it in as y in this y equals mx plus b calibration relationship and solve for x. We want to do that in Excel, and we don't want to have to type in these numbers, because if we discover that one of our data points was faulty, we recorded it wrong, or we wanted to re-record that, we could replace it here and it would change it here, but it wouldn't change it in our sheet in the rest of our calculations. So we want to make this a living spreadsheet. So we're going to use the LINEST function. And in order to do this, you want to select a block of two rows and 3 columns and select the whole thing. Don't just select one cell. You want to select a block of cells and then start typing your function. So equals LINEST, okay, and it pops up there in your autofill. And then it'll prompt you for what you should be entering here. So you want your known Y values, right? So your Y values here are your absorption values. So for student A, I'm going to select all of the absorption values for student A. And then it asks for all the known X values, and those are my protein amounts. Then it has constants and stats here. Constants has to do with do you want to force the linear fit to go through 0? You can see that neither one of these actually go through the 0, 0 line, so they do have intercepts, y-intercepts that are not 0, and you generally don't want to force this to happen. So to not force it to happen, you say true. And then stats, there are other stats here we want other than just the coefficients, just the M and B coefficients. So I'm also going to say true to that. So I'm going to close my parentheses and not hit enter. So this is key. Do not hit enter. Hit on a Mac, it's a Command Shift Enter. If you're on a PC, it's likely a Control Shift Enter. Oh, that didn't do it. It's Control Shift Enter for me as well. Look at that. Okay. And it's going to give you an array of data here. So just I'm going to put in the 3 boxes here on the side and here on the other side what is in each one of these cells. So right here, you can already tell if you compare it to student A's calibration curve plot, right? That is the slope. For student A's calibration curve. And this other number on the right is the intercept. The 2 numbers in the cells right below the slope and the intercept are actually the standard deviation of the slope and the standard deviation of the intercept. So if you needed to propagate error, then you could do that because you have standard deviations associated with those numbers. Again, comparing to what's in the calibration curve plot, the R squared is 0.9938, and that is exactly what this number is here, this last cell. So that's your R squared value in that last cell. And then the bottom cell on the right is actually the standard deviation in Y. And so for any one of these points overall, like what's the variance, right, in your absorption measurements, that's what it turns out to be. So now that we have all of these values, right, from our calibration curve, but now they're in cells in a living manner, so I could change one of these. This would be like 0.4. Then that would also change the LINEST function's results over here. So that's helpful in case we need to change data. We don't have to redo all our calculations. And so now for student A, I'm going to calculate what the concentration of this unknown is by simply rearranging the y equals mx plus b expression. And so that means I'm going to have x equals y minus b divided by m. Okay, so you're just algebraically rearranging that. And so now I'm going to execute that as my answer, right, would be y, which is my unknown signal, my unknown measurement, minus the intercept, okay, divided by the slope. And so now there is my milligrams of protein in my unknown sample. Now you can check this just by inspection by saying, okay, if it was 0.276, it should be somewhere between these two measurements, and that's somewhere between 15 and 20, and so that answer makes sense. You'll also want to change the number of decimal places that are being exhibited here so that it's some reasonable number of sig figs, and we could do that for student B as well, and the answer might be different, right, depending on how well, because student B's slope is similar but the intercept is different, and so you're going to get a different answer here, and that would affect the accuracy of each student and whether they measured the same thing or not. So I'm going to execute LINEST here as well for student B. Known y values, known x values, true, comma, true, close parentheses, Control-Shift-Enter. Okay, again, I have all these same parameters, but now this is for student B, right? Okay, so this is student A, and this is student B. Okay, and then here again, I just want to make sure that I'm referencing, again, that unknown concentration, and there we go. So it's not too different, but it might be significantly different, and you'd have to do that for multiple trials to get an average and a standard deviation of your unknown sample.